That's totally true. All right, let's get started. So welcome everybody to the first installment of the online version of the New York Group Series seminar. So I hope that everybody is doing okay.
Thank you for putting it online, by the way.
Yeah, sure. So before I hand the microphone over to Zoran, let me mention that if you go to the webpage of the New York Group Series seminar, there are already several other, online Zoom talks, that are scheduled. Next week you'll have Sergey Merenkov. After that, it's Caroline Abbott. After that, probably Paul Schupp, if I manage to teach him how to use Zoom. And then later in April it will be Alexander Holtke. So several other talks have already been scheduled. So Zoran is going to say it, but I want to ask everybody that while Zoran is speaking, keep your microphone, which is the button in the lower left corner of your Zoom screen. Keep yourself on mute, so that you don't hear the background noise coming from your room, and only unmute it when you want to ask a question. So if you want to ask a question, so you're welcome to unmute it, so then we'll all hear the question. You can also send some messages during chat, but I don't know whether Zoran will have time to sort of to look at chat in real time.
Probably not. Probably not.
Yeah. So with that, it's a pleasure to welcome our speaker today. It's Zoran Sunik from Hofstra University, and he is going to tell us something about why deciding whether or not a right-angled Artin group is free by free is NP-complete.
Okay, thank you for the introduction. So what I will do is I will share my screen, and you will see the presentation slides basically, and I'll write on top of them from time to time when I want to make something more clear. And as already mentioned, I will actually mute everybody, and then whenever you want to, you can unmute yourself and say something. That way I will know that something happened. I cannot see most of you, which means just waving your hands will not be useful. So you have to say something if you want to interrupt me and ask a question, okay? So now let me share the screen. I hope you can see it. Nobody can answer now. Okay, I'll go under assumption that you can see the screen. So I'll be talking about deciding if a right-angled Artin group is free by free, and it turns out that this is an NP-complete problem. One of the main reasons I was interested in this problem was that it gave me a chance to produce a title with 4 hyphens, and I don't think I will ever do that again. Anyway, so this is based on some joint works. One is, well, fairly old, from 2007 with Susanne Hermiller, and another, well, not as recent anymore, with my former students David Carroll and Benjamin Francisco. So yeah, let's move on. We all know what a right-angled Artin group is. So right-angled Artin group, it's a group defined by presentation in which all relations are x, y, y, x. So some generators commute, some don't. That's all we know about the group. That's the entire presentation. And again, every presentation corresponds nicely to simple graph. Okay, whenever you have a simple graph, you take the vertices to be generators, and then whenever there's an edge, you add a relation that says, well, those 2 vertices, or more precisely, the corresponding generators, commute. Okay, so like you all know that, as I said. The easy examples and the obvious ones are when you have a complete graph, that means everybody commutes, your group is free abelian. When you have the exact opposite, the empty graph, the complement of the complete graph, then nobody commutes, there's no relations, so your group is free. And when some generators commute, some don't, you get something in between. There are some nice special cases, such as when your graph is complete bipartite, meaning m vertices on one side, in this case 2 on one side, and n vertices on the other side, 2 on the other side, and then you just let everybody in one group commute with everybody in the other. Well, of course, the group is just direct product of free groups. Okay, so those are the easy and obvious examples. There are many more well-known examples of right-angled Artin groups that have very, very simple structure, such as the famous pure braid group on 3 strands. I mean, B3 is the braid group, and then the pure braid group is the kernel of the map from the braid group to symmetric group. Like I said, these are all very well-known things. The point is that the pure braid group is just direct product of free group of rank 2 and Z. And more importantly, then this group is then virtually free by free, okay? But the pure braid group itself is right-angled because it can be given by this kind of right-angled type of presentation. T commutes with both A and B, and that's it. Less known right-angled Artin group, which is free by free, is based on the path of length 3 or path with 4 vertices. A simple way to see that this is actually free by free is to, well, add relations. Okay, here's the original group given by the commuting relations. So what we do is we introduce extra relations. The idea is to crush this entire path into a single vertex. So we introduce relation A inverse T, introduce relation B inverse T, and introduce relation C inverse B. That will make all the generators equal, of course. And what is the effect here? So I don't need these 3 generators anymore because I can express them all in terms of T. They're all equal to T. And A and T already commute because they're equal. They're equal, they're equal. So there's no more relations. So of course the quotient becomes Z. And what is the kernel? The kernel is, well, generated by, it's the normal subgroup generated by the 3 relations that I added. But you can prove that this group is actually free. This kernel is free in this case, and therefore your group is free of rank 3, semi-direct with Z. Okay. Okay, another example that I want to show you, and it's important to show you all these examples because they play a role later. So very, very simple example. If you think about this group, so again, here's the graph. Oops. Okay, there's the graph, very simple graph with 3 vertices. One way to write this group, of course, is to say this is copy of Z, which corresponds to A, free product with Z square, which corresponds to the generators B and C. But that's not what we want. We want to represent this group as free by free. So what we will do is same thing as before. We'll introduce some relations until we see a quotient which is free. There's a very simple way to do this then. All we'll do is we'll kill the vertex C, or we'll add relation C equal 1. Once I do that, that disappears, and that means that my quotient is a free group of rank 2 generated by A and B. And what is the kernel? Well, the kernel is the normal subgroup generated by C, the generator that I killed. But the problem here is, okay, what is the normal group generated by C? C commutes with B, so that's not a problem. When I conjugate C by B, nothing happens. But when I conjugate C by A, all these guys, I have to take them in the kernel. And then it turns out, yes, the kernel is free in this case, but it's infinite rank. So in other words, sometimes when we deal with free by free groups, we actually allow some of the terms in this decomposition to be infinite rank. Okay. And it will turn out, for example, for this particular example, even though it looks so simple, there is no way to write it as a 3x3 group of finite rank, no matter how you try. Okay, so you have to use groups of infinite rank. Okay, so more generally, then we are talking about what is called poly-free groups. A group is poly-free if there exists a series of normal subgroups from identity going all the way up to G. Maybe easier way to think, at least for me, is like this. On the top, I have the group, which is Gn. On the bottom, I have the trivial group. And the main point of the definition is that each of these quotients, when I go from one step to the next, each quotient is free group. Okay, so each factor is free. It's worthwhile to notice that, okay, so each time you have one of these quotients, since the quotient is free and the free groups are free, there's always map going the other way. So all these extensions are always split extensions. So to say that a group is poly-free is same as saying that the group can be written as an iterated semi-direct product of free groups. Okay, in other words, the extensions are always split. Okay, so that's the definition of a poly-free group. And in some sense, let me skip directly here. There's open question that I still think is open. Are all Artin groups virtually poly-free? That's the question, which is motivated by many examples in which obviously the answer is yes. I already alluded to some of those examples. So there's this fairly old result by now that describes many pure Artin groups of finite type and says that they're all poly-free. In particular, we already mentioned the braid groups. So the pure braid group is always poly-free, and which makes each corresponding Artin group virtually poly-free. Okay, and then there's also one of the examples I showed you at the beginning was this path of length 3. And I kind of tried to convince you that in that case the group is F3 semi-direct Z. It's more general than that. Droms already proved in 1987 that if the defining graph is 3 on n edges, then your group is semi-direct product of a free group of rank n and Z. So that thing is true for every tree, and the proof is always the same. You have your tree, crush the entire tree into a single vertex, that will give you a quotient Z, and look at the kernel will be free of rank exactly the number of relations you added, because you just identified n neighboring vertices, basically, okay?
So how hard is it to prove that the kernel is free in this construct?
I don't think it's very difficult. No, I mean, that's not the main result of this paper by Droms, okay? It's not too difficult, yeah. I'm just showing it as an important example because I will use it later. That's basically what I'm doing here, okay? Okay, I think Ilya already turned off his mic. All right, so move on. Well, there's a general then result. Let me go back. The question of Bestvina was about all Artin groups. Are they virtually poly-free or not? Now we will concentrate only on right-angled Artin groups. And we'll study this question of poly-freeness just for right-angled Artin groups. Again, it's an old result by Duchamp and Kropp that well, some parts in this talk will be true for infinite graphs, some will be true only for finite. Sometimes I will forget to tell you which is which, but bear with me. So if the graph is finite, of course, it will have finite chromatic number. Chromatic number is the smallest possible number of colors that you need to color your graph in such a way that no two neighboring vertices have the same color. So that's invariant of the graph. And another invariant of the graph is the clique number. The clique number of the graph is the largest possible complete subgraph that you have inside your graph. And this result simply says that the polyfree length, the shortest length of this polyfree, of this series of free quotients that you can have for your group, that's called polyfree length. And this result says, well, it's always between the click number and the chromatic number. The fact that it is bigger than the click number, it's more or less obvious. I mean, if you have, and I don't even think they mentioned it in their paper, but nevertheless, it's a simple result. If you have, say, K4 inside, that means that you have Z4 inside. And the problem with Z4 is when you try to decompose into a semi-direct product of free groups, no free group can contain more than single copy of Z. There's no Z square anywhere. So you have to do it in 4 steps, okay? So again, there's more to be said than that, but that's an easy exercise really for IDEA. That if you contain Z to the n, then your polyfree length must be at least n. The other end of the other inequality is perhaps more fun, but I even indicate here, the proof is simply you go by induction on the number of colors, and at each stage you just kill a color. So let me illustrate it with pentagon group, okay? If I look at the pentagon, this is a 3-colorable thing. In this case, the colors are black, white, and square. So on this pentagon that I have, I already colored it by using 3 colors. And I'm just saying, how do you prove that this is now free by free by free? I say kill one color, let's say X and Y. So X and Y are dead. This stands for dead. And once I kill X and Y, I'm left with, well, I'm left with our old friend. You see in the quotient, I have this group generated by A, B, and C that I already showed you before. That one was free by free. And what is the kernel? The kernel is, well, I killed X and Y, so the kernel is the subgroup generated by, the normal subgroup generated by X and Y, and you can prove that that one is free. Again, not completely trivial, but not too difficult either, okay? So in this case then, since I have 3 colors, I can do this in 3 steps, okay? And in general, you can, again, you can prove that the kernel of this map, when you kill a color, is always free. But let me point out, I already alluded to that before, it is always free, but it is rarely finitely generated, okay? Okay, so let's go to now characterizations of polyfree length in terms of the defining graph. The first proposition is obvious, trivial. A right-angled Artin group will be free if and only if G is totally disconnected. There's no edges whatsoever. Because as soon as you have edges, you have Z square inside and you're not free. Okay, so that part is clear. So there's a full and very simple characterization of the case when your Artin group is, right-angled Artin group is free. Okay, so move on to the next one. We are now interested in polyfree length 2. And of course, we want a proposition of this form. A right-angled Artin group is free by free if and only if something is true about the defining graph. And to relate it to the note before, free by free really means that there's always a quotient, which there's always a, starting with your group, you can find the surjective homomorphism to a free group such that the kernel is also free. So you have free group in the quotient and free group in the kernel. And this will always be split, actually. Your group will be always, at the end, it will be the FK semi-direct FQ. Okay, so now we are interested in this. And for which graphs I can do this?
K here is allowed to be infinity, right? You know, even
yes, exactly. When K is in, well, when the graph gamma is finite, of course FQ will be finite. I mean, Q will be finite, but you cannot guarantee that K itself will be finite. Yeah.
Okay.
Okay. So we are interested in basically kernels of maps to free groups, but to start the ball rolling, one has to go back to kernels of maps to Z, which is actually very old and interesting topic in right-angled Artin groups. I mean, you know that by studying maps of right-angled Artin groups to Z, Bestina and Brady proved that FP2 does not imply F2, and even earlier, you can sort of think of theorems of Stallings and generalization by Bieri that kernels of maps of right-angled Artin groups to Z have very, very interesting finiteness properties, okay? But that's not important for us. For us, at the moment, only these much simpler properties are interesting. Here's a criterion under which conditions the kernel of a map to Z will be finitely generated. Well, the result simply says that the graph should be connected, okay? Well, I'm lying here a little bit, but not too much. Well, on the slide, I'm not even lying. You see, I'm saying if the homomorphism is given by every generator goes to the generator of Z, then this is absolutely correct. If you allow some generators to go to 0 and some to go to 1, then you have to say the kernel is finitely generated if and only if the subgraph induced by the vertices that survived, the vertices that are not killed, has to be connected, and then there's additional conditions. So again, don't worry about that. I will only need this result in the form it is written. And in the form it is written, it says if you send everybody to the generator of Z, then this is certainly true. The kernel is finitely generated if and only if the graph is connected. And the second theorem here that says, well, that same kernel is finitely presented if and only if your graph is simply connected. And when I say here the graph is simply connected, I mean in the sense of simplicial complex, okay? So whenever there's a triangle, I can fill the triangle, okay? And that is simply connected. But when there's a square, I cannot fill in that one. And this one is actually not simply connected, okay? So we have very, very simple then criteria when this kernel is finitely generated or finitely presented. That's the point of this slide. And now we have this result with Suzanne that says, well, if I have nice map from my right-angled Artin group to a free group, surjective, and if the kernel is free, then I have a characterization of the graph. The graph contains a set of vertices which is totally disconnected as a subgraph of my original graph. And the other condition is that that set breaks every cycle in my graph at least twice. In other words, every cycle contains at least 2 vertices from that cycle, okay? From that set D. Again, there should be a special set D which induces totally disconnected subgraph, so no vertices in D are neighbors in the original graph. And that's one condition. And the second one is that every cycle meets this set at least twice. And there's no mystery what set of vertices that D is. It's basically the set of vertices that are killed by this homomorphism, okay? Our homomorphism will, of course, leave some generators alive, not kill them, not send them to 1, and some will be killed. So I'm saying that special set of vertices that satisfies this condition will actually be the set of dead vertices, the vertices that are sent to identity, okay? So that's a fairly simple criterion, I would say, that tells you exactly when your right-angled Artin group is 3 by 3. So we call that property of the graph. So now we have property of the group is it's 3 by 3. Property of the graph is what I just said. A graph is doubly, and we give it a name. We call it a doubly breakable cycle property. So that's the property. Here I have example on the slide. This is example of a graph that has doubly breakable cycles. Indeed, if you remove this set D, if you remove it, of course you remove all the edges that are neighboring to it, and what is left is just a forest, okay? Because remember, one of the conditions was that every cycle has to contain at least 2 of these dead vertices. Therefore, once I remove them, I'm left with a forest. There's no more cycles. Okay, so that's generally what you have to have in mind, what happens, okay? Once you remove this special set of vertices, you're left with a forest. Okay, so let's kind of try to indicate fairly quickly why I have to break all the cycles. Well, if I somehow allow a cycle inside my graph, so my graph is complicated. It has other things around, okay? But assume for a moment, ignore whatever else happens. You see, if this big kernel is free, then when I concentrate on some cycle inside, and I look at the restriction to that cycle, that kernel better be free too, because the kernel of this smaller map is a subgroup of the kernel. Again, there's a gamma goes to free group by phi. So that big...
Zoran, so in this picture, the cycle C, is it supposed to be an induced subgraph or not?
Not necessarily. It just has to exist inside somehow. Yeah,
so
good point.
In this C, there could be some chords, right? You know,
there could be. They will not bother me in the argument. Yeah, but good point. This is not induced. It's just some cycle inside. Okay. And by the way, the theorem said you have to break all the cycles, regardless whether they're induced or just exist inside. Okay. So yeah, good point. Anyway, so we have this map from the big group to F. We call it phi, and we are assuming the kernel is free. Therefore, when I restrict to the cycle, the kernel will still be free because it's a subgroup of that original one. So I can concentrate on this kernel, what happens with this kernel. But that's something we kind of already discussed. Well, let me convince you that we already discussed it. So the point is, none of this now, vertices, when I send it to F, is dead, okay? Because this cycle is not broken, none of the vertices is dead in F, in the image. But then you said this guy and this guy commute in the original group, therefore they have to commute in the image. So there are non-trivial elements of the free group that commute in the free group, and we know that that happens only when these guys come from a same cyclic group. But then this guy and this guy commute, and again, both of them live inside the free group, and both of them are non-trivial. Therefore, they all live in the same cyclic group. Actually, all 3 of them live in the same cyclic group because of this transitivity of the commutativity property, and so on. So you can conclude that actually all of these 6 guys, everybody in this cycle, when you go to the image, they all live in the same cyclic group. In other words, I can go back to discussing what happens when I map something to Z. But when I map something to Z, well, on this kernel is always, according to the theorem by Mayer and Van Dyck, because this graph is connected, the cycle is connected, that kernel is finitely generated. But this is not finitely presented according to Bestrina and Brady because this is not simply connected. Of course, you can say, wait a minute, if this cycle was a triangle, this would be simply connected. Sure, but I already know from a long time ago that I cannot have a triangle in my graph. Remember, our assumption is if my group is 3 by 3, then I'm trying to convince you that the graph has some properties. Since this is poly-free length 2, I know that I cannot have z cube inside, so there's no triangles anyway, okay? So
just a second, sorry. I mean, I don't understand this argument, because I think that this argument only works if C is an induced cycle, because if there are some additional edges between these vertices, then we don't know whether the graph is simply connected or not, right? You know, what if it's a complete graph on these vertices, for instance?
but it cannot be complete, because then there will be triangles.
And what about them?
Again, I cannot have triangles in my graph.
Why?
Because my group is 3 by 3, which means it's length 2. And the shortest way to do triangles is by length 3. Because I will have z cube inside.
Oh, I see. Ah, yes. Okay. Yeah.
Okay.
Good point. Thank you. That. Okay. Good. So the induced graph on C cannot actually be simply connected, right? Even if there are additional edges. I see.
Okay.
Okay. Yeah. Thank you.
All right. So anyway, then the real question is, okay, you have to break every cycle at least once, but why you have to break it at least twice? Because that's what the theorem said. You have to break everything twice, at least. That part of the argument is even simpler, namely, well, here's the cycle. What happens if I kill only this guy? Well, the argument is now really simple. I still have then that these guys are non-trivial once I send it to the image. They're non-trivial inside the free group, and this one commutes with this one in the image, commutes with this one, commutes with this one. In short, that means that the image of A and the image of B, they commute inside this free group, and they're non-trivial. Again, that means they come from same cyclic group, and that means that some element of this form, A to the M, B to the N, is in the kernel of my map phi. Okay, well, that's trouble, because D commutes with both A and B, and that means that this is now Z square, and Z square is part of the kernel, and that's the problem, of course. The kernel was supposed to be free. So that's that part of the argument, okay? So in short, that is telling you that if, that if you have something like this, then your graph has to have this property, doubly breakable cycle property. Now, going back to, yeah, if I now think about pentagon group again, remember I told you the pentagon group is 3 by 3 by 3 because it's the graph is tricolorable. Now I can say, actually, I can do it in 2 steps. I don't need to use all 3 colors. What I can do is the following. The pentagon is doubly breakable cycle. I can kill X and Y just like last time. And when I kill X and Y, I'm left with the graph right there, which of course it's not generating a free group. So just by killing X and Y, I'm not getting a free quotient. To get a free quotient, what I will do is, there's this annoying part, but I'll get rid of that by equating B and C. I'll add another relation, make B and C equal, therefore crush this thing to a single vertex, and therefore my quotient will be free of rank 2. And what is my kernel? My kernel, well, X was killed is in the kernel, Y is killed is in the kernel, and I added one more relation, B equals C, that is in the kernel. And then the kernel will be just normal subgroup of that, but you can prove that that thing is free. So the pentagon group is actually 3 by 3. Okay. Yeah. On the other hand, here's a graph where what is the similarity between the two examples? In this example, the click number is 2, the chromatic number is 3. In this example, the same thing, the click number is 2, the chromatic number is 3. But here, in this other example, there's no shortcut. I cannot really do this in 2 steps. I have to do it in 3 steps. And the proof is very easy. As you can see, this graph is very symmetric, it's homogeneous, so I can start wherever I want. So let's kill some vertex. Let's kill this one. Since I have to break this 4 cycle at least twice, that means that in addition to this vertex, I must kill this vertex. But in order to break this cycle twice, that means I have to kill this vertex. To break this cycle twice, I have to break this. I have to kill this vertex. Remember, the vertices that I'm using to break my cycles must not be neighbors. So that's the crucial thing. And here, in order to break this cycle, I have to, well, now I'm in trouble. I have to kill this vertex in order to take care of this cycle. But then I have a problem in this cycle because these guys that are both dead are neighbors. So I cannot actually find a subset of vertices in this graph that satisfies the conditions. So for this particular graph, even though it doesn't have z cube inside, I still have to do it in 3 steps. It's 3 by 3 by 3, but nothing shorter. Okay. And the general construction, I think by now it should be obvious. If I have a graph with the desired properties, I just kill the set of vertices D. I'm left with a forest, and in that forest, all you have to do is, well, there's several trees, just crush every tree individually. So add relations that say X, Y. So in this component, make all the vertices equal, add those relations. So in the quotient, after you do that, because I have here 4 components, in the quotient I'll have free group of order rank 4. In the kernel, what I will have, of course, is all these D guys, because I killed them. But in addition to all these D guys, in the kernel I will have XY inverse for every edge practically in the forest of the quotient, okay? In any case, you can prove that that will be still a free group. So this is 3 by 3, okay? That's the other direction of that result. So again, now some people are kind of saying, I don't care about infinite rank free groups. I really want 3 by 3, but with both factors finite rank. Adding this non-trivial for technical reasons. I don't want to discuss the case where the group is just free of some finite rank. So I really want polyfree length 2. So the result simply says a right-angled Artin group is 3 by 3 with both factors non-trivial and of finite rank. This is what I said before. This is actually rare. The graph has to be either at finite 3, in which case, and we already discussed this example, in which case your group is 3 by z, or it has to be a complete bipartite graph. And we also discussed this example before, and in that case your group is just direct product of 3 groups. So there's no other 3 by 3 right-angled Artin groups with both factors having a finite rank. And the proof of this is actually subtle, a little bit complicated, but I can just point out very quickly, for example, why the pentagon doesn't work. So the reason the pentagon cannot be written as 3 by 3 with both factors of finite rank is as follows. So you look at the Euler characteristic of the pentagon group. Well, if I can write it as a semi-direct product of 2 free groups of finite rank, then the Euler characteristic will be just the product of the Euler characteristics of these 2 groups, which is what I have here on the left. But on the other hand, the Euler characteristic is 1 minus number of vertices plus number of edges, which of course for the pentagon is equal to 1, because I have 5 vertices and 5 edges. But now I have this product. This product is equal to 1. That forces both K and Q to be 2, which will then mean that I can generate my pentagon group by using only 4 generators. But of course, we know that we cannot generate the pentagon group by using only 4 generators. We need at least 5 because the abilization of the pentagon group is Z5. Okay, so that's a simple argument to convince you that the pentagon cannot be done as 3 by 3 with finite rank. If you want to prove it in general, then of course it's subtle, and you really have to prove eventually that the only graphs that work are trees and complete bipartite graphs. Okay, so going back to the title of the talk, remember I'm supposed to talk about some NP-complete problem. So let's now go back to everything is finite. So the graphs will be finite and so on. And we have this result, we have this description under which conditions our group is 3 by 3. And I would like to point out that there's obvious tension here. You see, the set that I need to have, the set of dead vertices, has to be on one hand, it has to be large, because I have to break every cycle at least twice. On the other hand, that same set has to be very small, because in some sense it has to be totally disconnected in the group. There should be no neighbors. Okay, so it's, of course, individually it's easy to satisfy either of these two conditions. If you take very small d, it will be totally disconnected. If you take very large set d, well, it will break all cycles. But the point is that you want to do this simultaneously. And that's one point. So there's already something interesting. And on the other, if I give you a candidate for such a set, of course, it's very easy to check whether such a candidate satisfies the two conditions. If I ask you, here's a graph, here's the set D, does it break all the cycles at least twice? You go through the cycles and you figure it out. And even easier, is the graph totally disconnected inside the original graph? Sure, you can check quickly those two things. But if
just a second. So why is it easy to list all the cycles? I mean, it seems like a messy procedure.
I'm not saying it's not messy. I'm just saying it's polynomial. It's a polynomial algorithm to check if all the cycles are met at least twice. Yeah.
Okay. Trust you on this. Yeah. Okay.
Well, I think so, at least. But again, the point is, it's certainly much more difficult, at least seems much more difficult, to find appropriate set D, okay? And that's the point here. So in general, then, our claim here is that the problem of deciding if a right-angled Artin group is given by a finite simple graph is 3 by 3. We claim it's NP-complete. Without going to too many complicated details about NP and so on, I will not be very, very precise, but again, NP problem is a problem for which you can check quickly if somebody gives you candidate solution or so-called witness. You can check in polynomial time if that candidate is actually a solution. A problem is NP hard if every instance of every NP problem can be reduced to an instance of your problem in polynomial time. And it's NP complete if it is both NP and NP hard. And as we all know, if you can solve any NP complete problem in polynomial time, that means you can solve any other NP problem in polynomial time. And there's the famous question, is NP same as P? I don't know, but my point is that this fairly algebraic problem, the problem of deciding if a right-angled Artin group given by finite simple graph is 3 by 3, that problem is actually NP-complete. How do I convince you that this is the case? Well, the only reasonable way to prove that some problem is NP-complete is to reduce your problem to some, no, the other way around, to reduce some known NP-complete problem to your problem. Therefore, if you know how to solve your problem quickly, you can solve the other problem quickly, but the other problem is already NP-complete, okay? So,
but this proves that it is NP hard, right?
well, if in addition your problem is NP, which I think I claimed it is, that it is easy to check if a candidate breaks all the cycles.
Okay. Mm-hmm.
So again, what do? To answer even the question of Ilya, how do I check that all the cycles are broken? Well, I remove the set D that is candidate from the list of vertices, and I remove all the edges associated with it, and then I'm left with a graph. Now I have to check that that graph has no cycles, that it's just a forest. That's very easy, I would say. Okay. And then there's this thing, okay, I have to break every cycle twice, but that also is not a big deal, okay? So you're right, Olga. If I reduce non-NP-complete problem to my problem, that just means that my problem is NP-hard, but I'm saying in addition, my problem is NP, so that makes it NP-complete.
Okay, okay.
Okay. Okay, so very well-known NP-complete problem is the tree satisfiability problem that goes as follows. Given some arbitrary formula in conjunctive form, and in this conjunctive form, every term, every clause, so-called every clause, has exactly 3 terms. So we are supposed to, and these terms, by the way, some of them can be negations. So, for example, this last term could be x or y bar or z. Okay, so each term is variable or negation of a variable. So when you look at these kind of formulas, the question is, well, is there any assignment of truth and false to the variables that will make this formula true? Can you assign values to all the variables to make the formula true? And that's known to be NP-complete. It's actually, it looks easy, but it's not. Okay, so for our purposes now, what we need is, we need to prove that we can reduce any problem like this, any instance of that problem, we can reduce it to a problem in our world, so we can build a graph such that the original formula is satisfiable if and only if our graph has doubly breakable cycle property, which of course now we know it's equivalent to claiming that our group is 3 by 3. Okay, so again, the problem reduces to, given arbitrary formula, construct a graph such that the formula is satisfiable if and only if the graph that you constructed has the doubly breakable cycle property. Okay, so let me go immediately to the construction then. I think we started slightly with 5 minutes late, so I don't need more than 5 minutes to finish anyway. Okay, so again, let's see where we are. We are given a formula.
You officially have until 6 o'clock, actually. You know, even if you hadn't started late, so you're fine.
Okay, then even better. But there is enough time. I will actually finish. So again, where we are. Given the formula, I want to build a graph. And this graph has to have the property that the formula is satisfiable if and only if my graph has this strange doubly breakable cycle property. So the way to construct that graph is as follows. So for every variable that appears in my formula, I will have one of these 4 cycles. So for every variable, I have this 4 cycle that is called, we call it variable gadget. Okay, so there's one gadget for every variable, and it's a 4 cycle. For every clause in your formula, remember your formula may have many clauses there. So for every clause, I will have a pentagon, a 5 cycle. So, oops. So that's again, 1 5 cycle for every clause in the formula. oops, oh, sorry. And now, of course, I have to connect my variables to the clauses somehow. So here's a typical clause, X or Y or Z bar. So the way I connect, so the gadget for that clause, this pentagon, is connected to the variable gadgets simply as follows. V1 is connected to X because X appears in my clause. V2 is connected to Y because Y appears in my clause. And V3 is connected to Z bar in the variable gadget because Z bar appears in my clause. Okay, so it's a very, very simple way to connect things. In other words, let me be precise. In my clause gadget, I have 3 special vertices that are consecutive, V1, V2, and V3. V1 will be connected to its own variable, to the first variable in the clause. V2 will be connected to the second one, and V3 will be connected to the third one. But of course, I have to be careful. When the third one is Z bar, I connect it to Z bar. When the first one is X, I connect it to X, okay? So far, so good. I think should be clear. It's very, very simple construction. 1 4 cycle for every variable, 1 5 cycle for every clause, and then you just connect things more or less in the obvious way. Okay, so yeah, you can really read X or Y or Z bar. There you go, X or Y or Z bar. That's how this clause is connected to its own variables. All right, so that's the construction. Of course, there will be many, many more pentagons, 1 for every clause, and perhaps even more 4 cycles for the variables, but this is how to build the graph. Okay, now let's move on. So now I want to prove that once I constructed this graph, the graph is doubly breakable if and only if the original formula is satisfiable. So remember, the original formula has the clause C1 and many other clauses perhaps, but let me concentrate on one clause at a time. Imagine that my graph has this doubly breakable cycle property. In other words, I can color the vertices of this graph in black and white and think of black as being the dead vertices, and the dead vertices must not be neighbors to each other, and they have to break all the cycles twice. So assuming that my graph is doubly breakable, I will color the set of vertices that breaks all my cycles at least twice in black. And as soon as I do that, okay, I color all my vertices from the set D in black, that gives me assignment of truth values to all the variables, because you see, in the variable gadgets, exactly 2 vertices will be black and exactly 2 will be white. And I don't know, in this particular gadget, obviously Y is false because black corresponds to false and Y bar is true. And in this one, well, Z is obviously true because it's white and Z bar is false, okay? So again, once I color my graph, because the black vertices divide break every cycle twice at least, in all these 4 cycles, it will give me unique assignment of truth values to my variables. But now I still have to convince you, sure. So given the graph and given this set D, I got some assignment of truth values to my variables. But now I have to convince you that the formula actually is satisfied. Well, I claim it is satisfied. Well, assume it's not. Assume that the formula is not satisfied. What does that mean? That means that in this long formula, there must be a clause that is false after I assigned all the variables. And without loss of generality, assume that it's the first one, namely that this clause was false. Okay, so again, I already colored my graph, by using the vertices from D, and I know the graph is doubly breakable. And the black vertices gave me false, and the white one gives me true for the variables. And I claim that the formula now must be satisfied, but I assume by contradiction it is not. And if I assume that it is not, there must be a clause that is actually false. And let's say this first clause, without loss of generality, is false. That means X is false, yes. Y is false, fine. And Z bar is false, fine. That's exactly what I have on the picture. But now I have a contradiction because these three guys, X, Y, and Z bar are black, the neighboring vertices must be white. And now I have only two more vertices left in this pentagon, and I'm supposed to break this cycle twice. Remember, the original assumption was that G was doubly breakable and that the set D actually breaks all the cycles at least twice. So now I'm in trouble. I cannot really break all the cycles at least twice. So I have my contradiction. So it's impossible for the formula not to be satisfied with this particular assignment of truth values. Well, that's only one direction of what we need to do. We need to prove that if the graph is doubly breakable, then the formula is satisfiable. I also have to prove the other way around. If the formula is satisfiable, then the graph is doubly breakable, but actually this one has several cases, but it's really easy. And it goes the other way around. Let's say the formula is satisfiable. That means in any triple, in any clause, there'll be something true. And whatever is true corresponds to a white vertex in my coloring scheme. So as long as at least one of these neighboring vertices that are related to the variable is white, that gives me enough room here to put at least two black vertices. So I can actually finish the job. That's the main point. If, I don't know, I have many cases, here's one. Let's finish with this. For example, let's look at this one. The formula is satisfiable, that means it's true, that means this better be true, that means at least one of these three terms best be true. Let's see, in this picture, X is bad, it's false, Y is good, and Z bar is false, so these are bad. But again, I have at least one white vertex, which means now I have a room here to put a black vertex, and at one more black vertex in this pentagon, and I actually finished the job. I can color my graph in two colors and break all cycles at least twice. Okay, so that will basically finish that proof and prove that we have this NP-completeness. And let me just stop by saying that very recently I saw on Archive posted paper by Flores, Cacrobae, and Coberta that say, well, there's another NP-complete problem about right-angle Artin groups, namely, that's the question. The question, if there exists a surjective homomorphism from a right-angle Artin group to a product of free groups, basically is deciding the chromatic number of your group, of your graph, sorry. And it is already known that the question of chromatic number for a graph is NP-complete, so that will give you another interesting NP-complete problem about right-angled Artin groups. So let me stop here.
All right, very good. Thank you very much. So now I think people can unmute the microphones if they need to. Are there any questions to Zoran? So I had a
yeah.
I actually started to speak myself, but I don't know whether somebody else was talking. You know, so I mean, I was still not sort of completely clear on the simple part, you know, of your argument about how why the problem is in NP, right? You know, so you said that you remove the set D then you see that the remaining graph is a forest, which is easy to do. And then if it is, you still have to do something, right? Because that's, let's say the graph is a forest. That doesn't yet mean that the set D breaks every cycle exactly twice.
Correct.
You still have to do something, right?
Correct. That means that your set breaks all cycles at least once.
One, exactly right. Yeah, that's what he said.
How about twice? So let me share my screen. I actually skipped that little detail because I didn't want to go into such details, but let me share my screen again and go back to a picture of a doubly breakable cycle to explain exactly this point that you're trying to make. So when I defined doubly breakable, I had some picture of an interesting graph that is doubly breakable. I think it was this one, sure. So as pointed out by Ilya, very good. When I kill this set of vertices, of course, I have to be left with a forest. But that doesn't guarantee that every cycle was broken at least twice. That only guarantees that it was broken at least once. To break it at least twice, what does it mean for the original graph? For the original graph means the following, that say this vertex D1. The vertex D1, you see, in the quotient, or the forest, there's 4 components. Oops, sorry, that's 1 component. The point is that from D1, I must not have edge that goes to 2 different vertices in a single component of the forest. And that's the extra condition that you have to check.
And that's all that you need to check, right?
And that's all that you need to check, exactly.
Okay, very good.
Because that's the only way to make, how can D meet my cycles only once? I have to go in my component, travel through the component, and I have to go back to my vertex D. So that means that from that particular vertex D, there were 2 edges going to the same component.
I see. Okay, very good. Thank you.
And that's all I have to avoid. So you have perfectly good point, but I skipped over that detail when I was showing you that original.
So basically, the weakness for that the problem is in NP, it's going to be what exactly?
Well,
you have to be given a witness, and it has to be verifiable, like in polynomial time, right?
The witness is a candidate set D.
Of vertices, right? Okay.
Of vertices, so, exactly.
Okay.
So all you have to do then is remove those vertices from the graph and the edges that are related to it, and you'll be left with a forest. If you're not left with a forest, that's it. That's not a good graph. The candidate actually is not good. I don't know. The graph may be good, but the candidate you were given was bad. And if it is a forest, then step 2, check that one of the, for the original vertices that you deleted, none of them is connected by edge twice to the same component in the forest. And that's it. That's all very, very polynomial. Not even very high degree polynomial.
Yeah, right.
Okay, very good. Are there any other questions? Okay, let's thank Zoran then.
Okay.
For online.
Thank you, Zoran.
Thank you, Zoran. So I suggest now that even though we have a talk scheduled for next week, but if Zoran can leave this session open for a little bit, if people can want to talk to each other, now is the time to do it. Because
let's have wine and cheese now.
Yeah, exactly. So anyway, you can try to figure out how to do that digitally. Maybe a picture of wine and cheese or something.
Yeah. Well, I'm not sure if this format works, but that's the best I could do at the moment. So sorry.
No, it was like, I mean, it's very good. I think it's working very well. This is what we should do.
I have to start teaching next week by using this thing. So I was practicing on you practically.
When you're sharing something, so in Zoom, I haven't actually done it. Does it allow you to share like a specific screen of an application, or do you have
Okay,
to share?
let me share the screen and then show you. It's actually fantastic. You can share particular window. So instead of the entire screen, you can choose which window you share. You can share the entire screen, which I believe is what I did. And you can, there's a whiteboard, so you can share only the whiteboard and then you can write on the whiteboard.
Okay.
I guess if you have a tablet, you probably can write very well on the whiteboard, right? Because
I cannot. I don't have good handwriting, but some people can do excellent job. Sure. Let me show you the whiteboard. So let's see. If I share screen and I choose whiteboard and I share, there's a whiteboard, and now I can write on it. Once I fill the entire whiteboard, I can take a picture of it, and then later just make kind of a presentation out of whatever I was writing on the board. So I can make lecture notes at the end of the lecture.
Can you like these slides? Can we have them, like, or can we save them?
The slides, the talk.
Wait a minute. You've recorded the talk, right, Zoran?
I think so.
So I don't know. It would be interesting to see if you can actually then save it and somehow make.
I can save it in MP4 format, which is the standard format.
Yeah. It would be good. I don't know if I could get it. Then I might try to.
Yeah, I can share the presentation file. Sure, it's a PDF file, so there's nothing complicated to share.
Right.
Also,
I was interested in this MP4 file, because I would try to post it.
I can share that. I can share that. The host